Hi everybody. Our group number 5 will present the Kōan, which is called exactly the memory. So I will begin the presentation, and then my colleague Virginia continue the presentation. Here are some topics for consideration that we want to talk about. The first topic is what is memory? Memory from the point of view of machine learning. Then I will give some description of the problem, and then my colleague Virginia will tell you about the possible approaches to the problem of implementation of memory in artificial intelligence, about the morphology of the used robot, about description of the experiment, and then I'll tell you the advantages of using neural networks for the implementation of memory, and tell you about some fields of application of neural networks. So let's start. Memory. What is memory? Memory is one of types of mental functions and mental activities. It is designed to preserve, collect, and produce information. Then the ability to store information about the events outside of the world, and the reaction of the body for a long time, and ability to use the information to organize with individuals. This is the memory from the point of view of human. Human memory is associative. That means that some memories can generate a large area that is associated with them. One thing reminds us of another, and this one thing could remind us of the other thing. If we allow our thoughts, we will move from one object to another object, and we can get the chain of mental associations. In the artificial intelligence, for the information formation of associated memory, artificial neural networks are used. Besides the associative memory, there are better association memory. That means that at receipt of the stimulus by one set of neurons feedback, response appears on a different set of neurons. There are some machine learning methods. The first method is supervised learning. Supervised learning, that means for which president is taking care of situation and desired solution. The other type of machine learning is unsupervised learning. That means that for every president, only the situation is settled. You need to group objects into clustering given a parallelized similarity of data objects, and or reduce the dimensionality of the data. The third type of machine learning is reinforcement learning. One of the methods of machine learning in which the undeterred system, or maybe even an agent, is trained by interacting with some environment. Next, active learning. Active learning is characterized in that the learning algorithm has an opportunity to appoint the next situation to be studied, where the correct answer will be known. Next is semi-supervised learning. In case of semi-supervised learning, tasks and techniques are also made use of enabled data for training, typically a small amount of labeled data with a large amount of enabled data. The next is transaction. Transaction or transductive inference is a reasoning for observed special training cases for specific tests or maybe tasks. In contrast, introduction is reasoning for observing training cases to general rules which are then applied to the test cases. The next is multitask learning. That means the simultaneous training of a group of interrelated tasks, each of which are given their couples the same situation and desired solution. And the last is multivariate training. That means training when presidents can combine into groups. Each of these has present for all solutions, but only one of them, and we can know what of them has a pair of situation and required solution. So our phone, here we should test the hypothesis that an agent can perform a useful task with no explicit presentation of the world or the task. To implement distributed adaptive control like behavioral in a simulated mobile robot. And now I would like to give a word to my colleague Virginia, and she will tell you the rest of the presentation.
This slide, we will see an application of heavy learning in a simple robot. This picture shows how a neural network can be embedded in this robot. In this particular architecture, the proximity sensor and the collision sensor are distributed around the robot. Each sensor is connected to a node in the neural network. Well, the collision sensor are binary threshold. So if the input value is higher than a threshold value, the activation value is set to 1, otherwise it's set to 0. However, the proximity sensors are continuous. That means that the value depends on the state of the signal they get from the sensor. Well, the proximity layer is fully connected to the collision layer, and the collision in one direction, and the collision layer is connected to the motor action. The input of a node in the collision layer is described in the first equation, where C is the activation of the collision node, P is the activation of a proximity sensor, and W is the weight between the proximity layer and the collision layer. The activation of a particular node in the collision layer follows a threshold function, and the weights between the proximity layer and the collision layer can be described by the air equation, where eta is the learner rate, P is the activation of the particular node in the collision layer, P is the activation of a particular node in the collision layer. The mean of phase, the average activation of the collision layer. W is the square between the proximity and the collision layer. And epsilon is the forgetting value. This value is required because otherwise the weight of the weight will be too large over the time. Okay. The robot used in the simulation was the Pioneer mobile robot. It has a range of several proximity sensors around the robot. Only the front and the side and the sensor on the right side and the left side belongs to the neural network. The two distant sensors on the back are used only to avoid the robot becoming stuck on the camera. There are certain collision sensors attached to the proximity sensor. You can see the pose of the robot, and the wheels are individually driven by electrical motors. This robot has been tested in this environment. The environment consists of an enclosure with walls and a number of obstacles with different size and shape. Now I will share a video where you can see this robot interacting with this environment. So. Okay, can you see the video?
Yes, we can see it.
Okay. Where if the robot is moving forward, nothing happens. But if the robot starts to hit in an obstacle, the corresponding node in the collision sensor, the collision layer is active. And simultaneously, several proximity sensors in the proximity layer. So the connection between the proximity layer and the collision layer become stronger so the heavier learning. Every time the robot hits an obstacle, the corresponding node in the collision layer become active. And it will be extend the connection between the proximity node, the proximity layer, and the collision layer. At some point, this connection will start to avoid the robot hitting the obstacles. So you can see how the robot continue learning over the time. It will start to learn aware from every obstacle ever. Note that the robot has no information about of the model of the environment. They get the information they need through the interaction with this environment. We are seeing the robot interacting in different locations in the same scenario. Now we can see also the input vectors of the proximity sensor, the collision sensor, the activation of the collision sensor, the wave matrix between the proximity layer and the collision layer. Also the simple input of the collision sensor and the activation in the motor action layer. Now these are the last part of the scenario where we're going to see the robot is avoiding the obstacle. Okay, now I finished. So,
just in the end of the presentation, I would like to talk about the advantages of using neural networks for the implementation of memory. There are a few advantages. The first is that solving the problem with unknown patterns of relationships is much more easier. The second is that the resistance to noise in the input data of the neural network is much more high. The third, adapting to a changing environment. About this topic we talked in the ShanghAI Lectures. There was more material. The third, the potential ultra-high speed of the neural networks. And the last, robustness of hardware and implementation of neural networks. And the last screen, the possible fields of application of neural networks. Particularly in each subject area at a closed loop, we can find a problem that can be solved by a neural network. I found some list of special areas that could be the solutions of such problems has particular significance now. The first, economics and business tasks. Then medicine and healthcare, the third, avionics, then communications, internet, then production automation, political and sociological technology, and security and security systems. Then input and processing information and biological exploration. I think in all these areas there are tasks that can be solved by using neural networks, and there are much more areas where neural networks will be used in present. Then
Okay, thank you. So, a very nice presentation, guys. Really enjoyed it. And we now open up for questions from the audience, from the TAs, and from Fabio. Anyone want to start off? Okay, I'll start off with one question. So, can you say something about maybe a little bit about the limits of the learning you've implemented? Like, if you now put it in a different environment, would it still work? Or and if you now change, maybe some of the sensors got damaged, would it still work? Can you comment on that?
If some sensors are broken, it's still working because the neural network gets the information, so the interaction in a current environment. So they will continue learning, and at some point they will start turning away and avoiding the obstacles.
Okay, excellent. Any other questions from the TAs? We're running a little bit behind schedule here because we like to get in now group 3. Alvaro, yeah, there we go. Yeah, you raised your hand. Go ahead, Alvaro.
So, well, I'm curious about the time that the robot took for learning this avoiding obstacles behavior, and if they have any idea about how they can improve this learning time.
Okay. The only way to improve this learning time is changing and testing the values that we have seen in the question. And of course the sensors and the physical embodiment of the robot. Sorry?
Okay.
Yeah, okay.
Yep.
Can you hear me?
Perfect. Any other questions?
And the usual question, how was the cooperation in the group? Were just you and Elena, or also the other members cooperate?
No, only me and him.
Okay.
Okay.
And where you see the memory? So you think that your demo was successful, so that you really showed that at least in your case you don't need symbolic representation.
So, I can't understand you.
So
There's plenty of noise.
So where is the memory?
Well, I think the memory is in the connection between the proximity layer and the collision layer.
Okay. Good answer. Okay, thank you.
All right. Any more questions? No? Okay. Then thank you very much, Virginia and Lenya. Very nice work. And we'll move on to next group.